There are two designs proposed for a shaft of length equal to L and with a torque carrying capacity of T. Design 1 is a solid circular cross-section shaft of diameter equal to 40 mm, and design 2 is a thin walled circular shaft of average diameter equal to 40 mm. So this time we have a very thin wall, and for very thin wall the polar moment of inertia will be equal to 2 pi mean radius cube multiplied by thickness T. The thickness of the wall in design 2 has to be determined such that the maximum shear stress is same in both the design for given torque, so that the same material can be used for manufacturing both the shaft. So value of G is same, and condition is that we have same maximum shear stress. The ratio of the mass of the shaft using design 1, that is for solid shaft, to the mass of the shaft using design 2, that is for thin wall circular shaft, we have to find out. So let's consider here we have a solid shaft and one thin wall shaft, and this value here indicate the mean diameter and the thickness equal to T. We have a solid circular shaft as the diameter equal to 40 mm. So in this case value of D will be equal to 40 mm, and we have mean diameter dm is equal to 40 mm. So both diameters are same here, but this time it's a outside diameter and this one is a mean diameter. Thickness we have to find out. Condition is that for solid shaft and the thin hollow shaft the shear stress is remain same. So both these shafts have the same value of maximum shear. Even both these shafts have the same value of the torque also. Mass of the solid shaft will represent as ms and the mass of the hollow shaft will represent as mh. We need to find out ms by mh. To find out mass here we require the cross section area. The cross sectional area of the solid shaft will be equal to pi by 4 into d square, and cross sectional area for thin wall will be equal to circumference. Circumference is pi multiplied by dm multiplied by thickness T. It means that we need to calculate here thickness. Secondly, to find out torque here we require the polar moment of inertia. Polar moment of inertia for solid shaft is equal to pi by 32 into d to the power 4, and the polar moment of inertia for very thin wall shaft will be equal to 2 pi into rm, that is the mean radius cube of it multiplied by thickness T. This formula we have used in the welding. That will be same as equal to 2 pi. Rm we can write as dm divided by 2 cube of it multiplied by T. So this is 8 and this one is 2. So we'll get a formula for polar moment of inertia equal to pi divided by 4 multiplied by dm cube multiplied by thickness T. So this information we are having. So we use the condition here and we'll first try to find out the value of T. The maximum shear in the case of solid shaft will occur at radius equal to d by 2, and here it will occur at dm by 2. Now we have torsion formula here, that is we have T divided by J equal to maximum value of the shear stress R. That one is the outer radius. Now this equation can be rewritten as torque divided by the maximum value of the shear tau max will be same as equal to the polar moment of inertia divided by R outer value. In the case of solid shaft is same as equal to divided by outer radius, that is same as the mean radius in the case of hollow shaft, because the torque value and tau max they are one and the same value. Now J we have to substitute for solid is equal to pi by 32 d to the power 4. So we have pi divided by 32 into d to the power 4, and R outer is d divided by 2. So that 2 will shift in numerator equal to J for the thin wall is given as pi by 4. So we have pi divided by 4 into dm cube multiplied by thickness t, and we have outer value is a dm by 2. So we have dm divided by 2. So 2 will shift in numerator. So in this case, pi will be first get cancel on both sides. So 1 by will write here. This is d to the power 4 divided by d. That will be equal to d cube. 32 divided by 2 is equal to 16. On the right hand side, we have 4 and this one is 2. So 2 will come in denominator, and we have here dm square divided by 2 multiplied by thickness t. So 2 and 16, 8 will be left, and from this we can calculate the value of t. So 2 is get cancelled and 8 is left here. Okay, let's substitute at this point. We have d is equal to 40. So we have 40 cube divided by 8, and dm is also equal to 40. So we have 40 square multiplied by t. So 40 square is cancelled, 40 by 8 is 5. So t will be equal to 5. So in this case, we'll get a t value is equal to 5 mm. So required thickness will be 5 mm, and we want to find out here the ratio of mass of the shaft using design 1, that is solid shaft, to thin wall shaft. So we have ms for solid shaft and mh for thin wall is proportional to area, and area is pi by 4 d square. So we have pi divided by 4 into d square divided by, for thin wall shaft the area will be equal to pi into dm multiplied by thickness t. So pi will be cancelled, and we left here with d square. D square is same as equal to 40 square. So we have 40 square divided by 4 into dm is equal to 40, and thickness t is equal to 5. 40 cancel, 140 left, and 4 and 5 is 20. It means that this answer is exactly equal to 2 times. A hollow aluminum tube used in a roof structure has an outside diameter of 100 mm and inside diameter of 80 mm. The tube is 2.5 meter long and value of G is given as 28 gigapascal. If the tube is twisted in pure torsion by the torque acting at the end, what is the angle of the twist? In degree, you have to find out when the maximum shear permitted equal to 50. Again, you have to calculate the diameter D required for solid shaft to resist the same torque with the same value of maximum shear stress. So maximum shear stress for both cases is same, even the torque is also same. And in the part 3, we have to find out the ratio of the weight of hollow tube to the weight of the solid shaft. So comparison is to be done for the weight of solid and hollow. So let's consider we have a hollow shaft here with the inside diameter is equal to 80 mm and outside diameter equal to 100. The length is given as 2.5 meter. So we have L is equal to 2.5 meter. Value of G is given as 28 gigapascal. So G you have to take as 28 gigapascal. Torque for solid shaft and the torque for hollow shaft is same. Even the value of maximum shear in the case of solid shaft and the maximum shear in the case of hollow shaft is same. And this value of tau max is given as equal to 50. That will be megapascal. First part you have to calculate here what is the value of twist for hollow shaft. So phi h you have to calculate. Then we require to calculate diameter D for solid shaft, that is ds you have to calculate. And finally you have to calculate the ratio of the weight of hollow. So weight of hollow to the weight of solid. So these three values you have to calculate. Phi means same as equal to theta, that is the twist angle you have to calculate. Twist angle theta you can calculate as T multiplied by L divided by J into G. So let's first calculate here what is the torque. Torque for hollow shaft we can calculate as torque equal to pi divided by 16 into do cube into 1 minus k value. K value is same as d1 by d2 to the power 4 multiplied by maximum value of the shear, that is the value of tau max. So we have pi by 16. Diameter DO is same as equal to 100 cube into 1 minus d1 equal to 80 and value of d2 equal to 100. Power is 4 multiplied by maximum value of the shear stress, that equal to 50. So torque for hollow and the solid is known to us. So we get a torque equal to 5.796 will be 10 to the power 6 is Newton mm. 10 to the power 6 Newton mm is kilonewton meter. So we have 5.796 kilonewton meter. Once we know the value of T, we can find out theta. So we have theta equal to torque, which one equal to 5.796 into 10 to the power 6. Length you have to use here equal to 2.5 is 2500. Polar moment of inertia for hollow shaft is pi by 32. So 32 will shift in numerator. So multiplied by 32. It's a d2 to the power 4 minus d1 to the power 4 is 100 to the power 4 minus 80 to the power 4 multiplied by g, which is 28 giga. You have to use mega, so you have to multiply by 10 to the power 3. So we have theta equal to 0.8929. That will be radian. Multiply by 180 divided by pi, it will get in degree. So we get a value of theta equal to 5.12 degree. So theta is known. Next you have to solve for ds. Since we know the torque here, we can use formula for solid shaft. So for solid shaft we have torque equal to pi by 16 multiplied by diameter of the solid shaft q multiplied by maximum value of the shear, that is tau max. Torque again we have to put as the same as 5.796 into 10 to the power 6 equal to pi divided by 16. Diameter of solid shaft we have to find out. Maximum shear you have to use same value, that equal to 50. So the diameter of the solid shaft will come out to be 83.9 mm. And finally we find out here weight. Ratio of the weight and the ratio of the mass is same. So we have weight of hollow shaft to the weight of solid section is same as equal to cross section area. Pi by 4 is cancel, and we have cross section area for hollow is d2 square minus d1 square, and for solid it will be equal to ds square. Let's substitute. d2 equal to 100, so we have 100 square minus d1 equal to 80, so we have 80 square. Whole thing is divided by diameter of solid shaft, which one is 83.9, and we have to make a square of it. So the weight of the hollow shaft to the solid shaft come out to be 0.51. It means that the weight of the tube is 51% of the weight of the solid shaft. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.